Welcome to Multivariate Calculus. Today, we are going to explore one of the most fascinating and powerful tools in mathematics, the line integral. If you have ever wondered how to calculate the exact effort required to hike a winding mountain trail, or how to find the total mass of a twisted wire with varying thickness, you are in the right place. We will build this concept entirely from the ground up, step by step. So let us dive in and get started. To understand why line integrals matter, imagine you are walking along a winding hiking trail in the mountains. In basic calculus, you learned how to add things up along a perfectly straight, flat line. But the real world is rarely perfectly straight. On a mountain trail, the steepness changes at every single step. Sometimes you walk uphill, which is hard, and sometimes downhill, which is easy. A line integral allows us to chop that winding path into microscopic steps, figure out the effort for each specific step, and add them all up. It frees us from the straight x-axis, letting us integrate along any curve in space. Now that we understand the idea of walking along a curved path, let us look at the mathematical formula for a scalar line integral. Conceptually, this formula comes from multiplying a value at a specific spot by a tiny piece of length and adding all those tiny pieces together. The integral sign with the c at the bottom means we are adding things up along our specific curve. The function f of x and y represents the value we are adding up, such as the density of a wire in kilograms per meter. Finally, the symbol ds represents that tiny, microscopic piece of the curve's length. If the density increases, the total mass increases. If the curve is longer, we have more tiny lengths to add up. Before we move on to the full calculation, let us visualize exactly where this tiny length comes from. Look at the diagram on your screen. We have a curved path in the xy plane. If we zoom in on a microscopic section of that curve, it forms the hypotenuse of a tiny right triangle. The horizontal base of this triangle is a tiny step in the x direction, and the vertical height is a tiny step in the y direction. By using the Pythagoras theorem on this tiny triangle, we can measure the exact length of the curved path perfectly. This visual understanding of the tiny triangle leads us directly to the final usable formula for a scalar line integral. We cannot easily integrate over an abstract curve, so we parameterize it using time. We replace the abstract curve with concrete time limits, a and b. We replace the x and y in our function with our parameterized equations, writing them in terms of a new variable t. Finally, we replace the tiny arc length with our square root expression multiplied by the change in time. This square root expression is exactly the speed of an object moving along the curve. If the speed increases, the distance covered in that tiny time step increases. Now that we have our usable formula, let us see this with a concrete example. We want to find the total mass of a wire shaped like the top half of a circle with radius 2, where the density is equal to the y-coordinate. First, we need to parameterize the curve. We use the standard angle parameter t. For a circle of radius 2, the x-coordinate is 2 times the cosine of the angle, and the y-coordinate is 2 times the sine of the angle. Since it is a half circle, our angle goes from 0 to pi. Then we take the derivatives with respect to t to see how fast our coordinates are changing. With our derivatives in hand, we continue by plugging them into the Pythagorean formula to find the tiny arc length. We place the x derivative and the y derivative inside the parentheses and square them. Squaring negative 2 sine of t gives us 4 sine squared of t, and squaring 2 cosine of t gives us 4 cosine squared of t. We can clearly see a common factor of 4 in both terms. We factor out this 4, leaving us with sine squared plus cosine squared inside the parentheses. This sets us up perfectly to use a very famous trigonometric identity. Following that trigonometric identity, we know that sine squared plus cosine squared always equals exactly 1. This simplifies the complex expression inside the square root beautifully to just 4 times 1. The square root of 4 is exactly 2, meaning our tiny length piece is simply 2 times the tiny change in angle. This constant speed makes perfect sense for a circle. Now we set up the full integral. We integrate from 0 to pi. We replace the density function with our parameterized y equation, 2 sine of t. Finally, we multiply this by the tiny length piece we just calculated. Now we just need to evaluate this simple integral to find our final answer. We pull the constant 4 out to the front. The antiderivative of the sine function is negative cosine, giving us negative 4 cosine of t. Using the fundamental theorem of calculus, we plug in the upper limit of pi and subtract the result of plugging in the lower limit of 0. The cosine of pi is negative 1 and the cosine of 0 is positive 1. Doing the basic arithmetic, we get 4 minus negative 4, which equals 8. The total mass of the wire is exactly 8 units. Having mastered scalar line integrals, let us look at the second major type, the vector line integral. Imagine pushing a heavy cart along a curved track while a strong, unpredictable wind is blowing. This wind is a vector field, meaning it has a specific direction and strength at every single point. If the wind blows with you, it does positive work. If it blows against you, it does negative work. A vector line integral calculates the total work done by this field as you move along the curve. It uses the dot product to measure exactly how much the force is pushing in your exact direction of motion at every single step. This concept of calculating work brings us to the standard formula for a vector line integral. Conceptually, we are adding up the helpfulness of the force at every tiny step along the entire curve. The bold F represents the force vector field, like the wind pushing against you. The dr is a tiny vector pointing along the curve, representing your tiny step forward. The dot in the middle represents the dot product operation, which filters out any sideways forces. If the force aligns perfectly with your movement, the dot product is large and positive. If the force is perpendicular, the dot product is 0, meaning no work is done. To actually calculate this in practice, we must parameterize the curve using time, just like we did before. The position vector is written as r of t, which tracks where you are at any given second. We plug this position into the force field to find the exact force at that specific location. We replace the tiny step with the velocity vector, r prime of t, multiplied by the tiny time step. Then we take the dot product of the force and the velocity. If the velocity increases, you cover more ground in that time step, affecting the total work accumulated. Let us apply this parameterized formula to calculate the work done by a specific force field. We are given a force field and a particle moving along the curve y equals x squared from the origin to the point 1, 1. First, we need to parameterize the given curve. Since y is already a clear function of x, the easiest way is to let x be our time parameter t. This means y must equal t squared. This gives us a complete position vector. Because our x-coordinate moves from 0 to 1, our time parameter will also go from 0 to 1. Continuing with our setup, we take the derivative of the position vector with respect to time to find the velocity vector. The derivative of t is 1 and the derivative of t squared is 2t. This vector points in the exact direction we are moving. Next, we look at our original force field, which was given as the vector y, x. We must substitute our parameterized variables into this field. We replace the y component with t squared and the x component with t. This new vector tells us the exact force pushing on us at any specific time. Now that we have both vectors, we set up the dot product between the force vector and the velocity vector. We multiply the first components together and multiply the second components together, then add the results. We get t squared times 1 plus t times 2t. This simplifies beautifully to 3t squared. This single scalar number represents the exact amount of work being done at a specific instant in time. We then integrate this simplified result from our starting time of 0 to our ending time of 1, turning a complex two-dimensional problem into a simple one-dimensional integral. Finally, we evaluate this simple integral to find the total work done. The antiderivative of 3t squared is simply t cubed, according to the reverse power rule. We place this result in brackets to evaluate it from the lower limit of 0 to the upper limit of 1. We plug in the upper limit and subtract the result of plugging in the lower limit. 1 cubed is 1 and 0 cubed is 0. The final answer is exactly 1 joule. This positive result means the force field generally helped push the particle forward along its path, rather than fighting against it. So, we have seen how to calculate these integrals. But why do we go through all this effort? Line integrals are the absolute backbone of advanced physics and engineering. Without them, we could only calculate work done by constant forces moving in perfectly straight lines, which almost never happens in the real world. In electromagnetism, line integrals are used to calculate the voltage between 2 points in a circuit. In fluid dynamics, they calculate circulation, measuring how much a fluid swirls around a loop. This exact swirling calculation is how aerospace engineers design airplane wings that generate enough lift to fly. As we wrap up, let us review the key takeaways from our journey. First, a line integral allows us to add up values along a curved path instead of being restricted to a straight line. Second, scalar line integrals add up regular numbers to find physical quantities like the total mass of a curved wire. Third, vector line integrals use the dot product to calculate the total work done by complex directional forces like wind or gravity. By parametrizing the curve, we magically turn these complex multidimensional problems into simple integrals that we can easily solve. You now have a solid foundation in line integrals.